Hello, everybody. Welcome to CSE Bytes. CSE Bytes is a monthly event where our faculty members share the recent research, ongoing projects, and some cool ideas. As an audience, it's a great opportunity for us to know what is happening in the department, hear about works from other labs, and possibly even spark some cross lab collaborations. From this semester, we are also recording this event whenever possible. So if you or your friends have missed the talk, please feel free to go to our YouTube channel, the CSE department's YouTube channel, and you can find these talks there. So today, our speaker is C Sivaramakrishnan. Casey. Casey rejoined us as a faculty member since last year. Before this, he was a faculty member from 2019 to 22 here. Between 2022 to 25, he continued to be an adjunct professor here, but at the same time, he also worked on setting up his own startups, which have been quite successful. Now, he has co-founded several companies, including Taridays, OCaml Labs Consultancy, SegFault Systems, and from what I understand, all of them are now bought by Taridays. Got merged into Taridays. He is interested in building robust, secure, and scalable systems using programming language technology. He has led development of multi-core OCaml, a concurrent and parallel extension of OCaml programming language, and this will be available for general use from OCaml 5.0 version onwards. Casey did his MS and PhD from Purdue University. He was a senior research associate under OCaml Labs initiative at the University of Cambridge Computer Science and an 1851 research fellow at the Darwin College, Cambridge. Recently, he has also secured a CSR grant from Jane Street to IITM to establish FP Launchpad, a center for functional research programming, functional systems research and education. The grant provides 23 crores in support over a period of 4 years. You can talk to him more if you want to know about this. Today he will tell us about how to evolve OCaml programming language.
Thank you. Thanks, Anita. Thanks for that very nice intro. For those who are wondering, we have not invented a time machine, right? So this is just me like waking up from my own siesta in the afternoon. I didn't change the date. So today I just wanted to talk more broadly about OCaml programming language, what I do, what I have been doing for the past decade, almost 12 years now. So I'll sort of try to give you what excites me around this and possibly share, ignite some excitement in you as well. Right? So yeah, so again, some bits of who I am. I work on programming languages, form verification and systems. I'm also a core maintainer of the OCaml programming language. Which is what I will talk about a lot today. So I'm also a CTO at this company called Taridays, which works on the OCaml language and the ecosystem. We are the maintainers of the OCaml compiler, one of the maintainers of the OCaml compiler, and a lot of the platform tools. So does anyone know what this is, this particular IDE? Yeah, it's a Turbo C++ IDE, so which is where I learned to program C, right? And many of you may not even have been born by the time this was invented. But when I was programming C here many eons ago, I thought C language was perfect and final, right? Like the mountains and oceans, they're all like, somebody invented the language, oh, it's there. There are books, people have printed. How can it be that the language will evolve, right? But I grew up. I mean, then I learned about plate tectonics and all of these things where mountains and oceans also evolve over millions of years, right? Programming languages evolve a little bit faster. So the point of the talk is to sort of shed some light on how programming languages evolve, in particular the language OCaml, which I've been involved in, how that evolves, right? So that's the point of this main point of this talk. So I know many of you have heard about OCaml. I'll give you a little bit of a sense of what the language is, just to place it in context with the languages that you know. So it's a functional first programming language. People call it a functional programming language as well, but it can also do imperative features and object-oriented features as well. It is a statically typed language with type inference. It has many advanced features which industrial users really like. And we've recently added multi-core support and effect handlers to the language, which I will talk about a little bit towards the end. So OCaml is a very fast language. It can compile to native code directly. It supports many platforms, x86, ARM, RISC-V, and many others, Power, IBM S390X, which is a supercomputer platform. We can also compile there. Interestingly, OCaml can also compile to JavaScript and WebAssembly. So WebAssembly is this new assembly language for the web that is present in every browser. It provides a nice compilation target for high-level languages, which is much better than JavaScript. So we've actually, as part of the OCaml work, we've contributed to WebAssembly development as well. So there is a feature called WebAssembly GC, which OCaml is the first language to use. So it's at the cutting edge of language development as well. There are a bunch of platform tools to make you productive programmer when you use OCaml. And the ecosystem is not as large as Python or other languages. It's small but mature, right? And there are a bunch of companies which use OCaml. You may recognize some of them, but they all are not OCaml first companies except a few. But they use OCaml for very important aspects, right? And one of the primary aspects of OCaml that these companies like is OCaml is said to have what is known as a high dynamic range, which means you can write scripts in OCaml for throwaway things that you would write bash script for, but also build production quality systems, right? And this dynamic range is sort of one of the very reasons why industrial users like OCaml. I want to give you a couple of examples of where OCaml is used. So how many people have Facebook accounts here? Okay, old people have Facebook accounts, right? I have a Facebook account. Facebook is written in a language called Hack, which is a statically typed language on top of PHP. So original Facebook app was written in PHP, and once you grow to like multiple millions of lines of code, dynamically typed languages like PHP and JavaScript are not scalable for software development. People have realized this and they've invented static types on top. So Hack is a language that Facebook app is written in today, right? And Hack compiles to PHP, and the compiler is written in OCaml, right? So that is there. Initial version of the Rust programming language was written in OCaml, and there is WebAssembly. The reference spec for WebAssembly is also in OCaml. So if you want to contribute to this like world-changing technology, you have to know OCaml, right? So OCaml is used behind the scenes in a lot of these places. So it's not just compilers. Hrefs is a company which is a search engine optimization company. If you create your company and then you want your company to be top when your competitor name is searched, you will go to this Hrefs and say, how do I bid such that my company shows up top of the results? So Hrefs implements a lot of their systems in OCaml, but also their front end. All of the front end is also written in OCaml, compiled to JavaScript. On the system side, OCaml is a great systems programming language. If you use Docker for Mac or Windows, the reason it works on Mac or Windows trying to run a Linux VM is because there are OCaml libraries that are powering conversion of whatever communication that the Linux containers are doing down to your system, which is Mac or Windows. So there's a very nice paper that was published last year at ICFP that sort of writes about this experience. We've also launched OCaml into space. So Parsimony is a company that was a spin out of my startup. We built a really small hypervisor, an operating system layer that sits below, just on top of hardware, in OCaml for essentially sharing multiple payloads on the same satellite and providing isolation. So we launched a test satellite earlier last year. So it flew on a SpaceX rocket. There's a nice long shot of it where the rocket goes in and then the booster comes back. So some of the code that I wrote is there. Not all of the code was written by me. So the point is OCaml sort of sits in the sort of application stack. The avionics control and all is all in other languages, right? But a lot of OCaml code is running in space today. Yeah, this you might have all heard. Jane Street is a known company in this room. So They are one of the companies that use OCaml for everything. They have 60 plus million lines of OCaml code in production, all the way from like distributed systems to trading models to even writing hardware. So they use OCaml as a DSL for describing hardware, which they compile for deep packet inspection, right? So they want to make decisions really, really fast. They write programs that compile down to hardware, but the programs themselves are written in OCaml, right? So there's a wide range of things that you can do with OCaml. And you'd be surprised if you know that, if I tell you that OCaml is today 29 years old, right? It's a very old language. It's as old as this movie DDLJ. When I present this talk earlier, I always used to say OCaml was released when this movie is still running, was still running in the theaters. And someone corrected me. There is a theater in Maharashtra somewhere where this movie is still running. They stopped during COVID, they restarted it. So we will see how long we'll go. We are competing with DDLJ, so good competitor, right? Very old. I mean, just to give you an idea, this is the best-selling phone the year OCaml was released, right? So there is this tendency in tech to always go for new and shiny things, right? And the question that we want to ask is, this is a 30-year-old language. Is this still relevant today, right? And OCaml 1.0 was released in 1996. It had a lot of the nice features that people like and love today, even back in 1996. And in fact, the roots of OCaml go back much, much further, right? So some of the type system and type inference work that OCaml uses comes all the way from 1973, from Robin Milner's meta language. ML stands for meta language, for part of a theorem proving system called LCF. And then it's been still evolving, right? So we got OCaml 4.0 in 2012. In 2022, we got OCaml 5.0 with the multi-core parallelism and effect handlers. And if you sort of see, I mean, this should be 2026 again, there's 50 plus years of evolution of ideas, right? And in fact, we have 30 plus years of code, right? And the question that I want you to think about is, if you have 30 plus years of code, how do you sort of like, not just like survive, but thrive after 30 plus years, right? If you wanted to design a system today and you wanted to work 30 plus years from now, how do you think about these problems, right? And one of the key aspects why OCaml is able to do that is because of its simplicity and stability. So OCaml won the 2023 Sigplan Programming Languages Software Award, and Xavier Lewa, who is the creator of OCaml, highlighted a couple of things in his talk. And one thing he highlights why OCaml is really successful is the language has a very simple cost model. So you would be able to, if you are sufficiently expert, you would be able to look at the OCaml code, and you should be able to know how much time and space OCaml program takes, where the memory allocations are, how much, where the loops are. Everything should be very apparent while still remaining high level, right? So that is one aspect. The second aspect is that the compiler is actually quite dumb in OCaml. So compiler produces code that looks like the source code. And if you are expert enough, you can look at the OCaml code and predict what the generated assembly is. And why this is important is, you don't want a compiler to do smart things from the get-go, right? Then you won't have the model of how to optimize the program, what sort of decisions you make. But the idea that you have a very simple compiler means that if you want certain piece of code to go fast, then you put in the effort to optimize it in the OCaml land, and you will see a corresponding change in the generated assembly, right? So it's very, very simple and simple language, but it's also a very stable language. So if you take OCaml code from 20 years ago and you compile it with the modern compiler, it will still continue to work. This is not true with lots of other languages, right? You take code from last week in JavaScript and you use it now, things will break, right? The other thing that, what I'm doing here, I go to my friends who are in JavaScript community and then say, look, OCaml is great, go use it. They will look at the package ecosystem and they will say, this package hasn't been updated for 6 weeks, so the package is dead, right? It's quite the opposite. The package has reached its level of sophistication and necessity. I mean, it's sort of plateaued at the level at which it needs to be, and there is no more work to be done, right? we have this tendency in software that we have to constantly keep maintaining it, poking at it. It doesn't have to be, right? It can reach a stable state, it will continue to work. So a lot of the packages may not seem very actively developed. That is by design, right? That's not because they are no longer actively developed. And there is nothing to be done to keep it working. So we really seriously take care of backwards compatibility. So when the language evolves, we try to make sure we don't break existing code, right? A lot. So there is this tension between simplicity and stability and innovation and growth, right? As a language, we get newer ideas. How do you sort of balance this? You have to make a choice, and OCaml squarely falls in the bucket of simplicity and stability. So it is a conservative language. We choose to not do certain things just because they are very new, right? We don't know. So some of these features getting into OCaml, they will take a lot of time. But we like that because industrial users like stability, right? They don't like to change code. If you are an industrial user who has 100 million lines of code, you don't want to have that code breaking with every compiler update. So a bit on the human side of the evolution of the language. So OCaml, as I said, has a bunch of maintainers. So there are 27 maintainers across the world. OCaml started in France, so there is a lot of French people here. Bunch of people from UK, Japan, one from India, and one from USA. Across industry and academia, right? So there are lots of people here. And the important thing is that all of them are custodians of the compiler. So they are the ones who sort of gatekeep what features get into the compiler. They are not the only people who develop the features, right? So I think that's a very important distinction. These are not the people who decide, okay, OCaml has to evolve in this direction, we are going to do that. So these are the people who sort of say this feature which somebody else has developed can get into the compiler, right? And I should also say very few people on this list are paid to work on the OCaml compiler, right? They're all doing it in their free time, right? I'm not paid to work on OCaml in my job, right? My job responsibilities are something else. So I think, that's one of the reasons why we also don't want to develop the compiler ourselves, because we just don't have the time, right? So the question is, how does OCaml evolve then, right? Who adds the features, right? I want to convince you in the rest of the talk that you all can, right? Let's see how that goes. Before that, when languages evolve, there are several models of evolution. OCaml and in fact Python has this user-driven evolution. So users can propose features, right? You can ask for features. Better, you can implement the feature in the compiler and say, look, I've done this. Here is the feature for upstream consideration, right? So that is one way. There are also committee-driven languages like C and C++, where a closed committee meets and says they accept proposals, but the committee decides what features get in, right? And these committees are organized by standards bodies like ISO, right? And there is vendor-driven consensus. WebAssembly is an interesting setup. It's supposed to be a very open meeting, right? So WebAssembly meetings are all open. They're all usually online. You can just go in and say, oh, I want to work on WebAssembly support for GPU. There is a working group where you can join and participate in the discussions. But eventually the problem with WebAssembly is there are big vendors, right? Intel, Firefox, right? And Google. So they all need to agree on what feature should be implemented finally in the browser themselves. So they have sort of a soft veto, right? Again, this is not like encoded anywhere in the WebAssembly WebAssembly organization, but it's not a completely user-driven setup. The other distinction I want to make with OCaml is that the language and the compiler aren't distinct, right? So whatever version that you are running today defines the language that is accepted by that compiler. So 5.4 has a version of the OCaml language. 5.5 may have additional features, right? Hopefully we don't break backwards compatibility, but there is no separate language specification apart from the compiler, right? So this is sort of this is not fairly standard, which means that you can only have one compiler, and if you have two compilers for the same language, they are two different languages. In OCaml, OCaml compiler implementation, whatever the OCaml compiler implementation accepts is the language. This is very different from other systems like C, WebAssembly and JavaScript. In fact, if you want to know what C language is, you can pay some 25,000 rupees to ISO and download this PDF, right? And the PDF describes exactly what the language is. And you can implement your own compiler, GCC and Clang implement that compiler. So there is a distinction between the language and the compiler. In OCaml, it's the same thing. Why does it matter for this discussion? In OCaml, the bar is actually lower because you don't have to convince a language committee and then you don't have to convince the compiler implementers. You just go ahead and implement it. If the feature is good enough, the OCaml maintainers are going to say, okay, this is fine. This sounds like a good feature. Let's have it in the language, right? Yeah, so that's what I want to say here. I wanted to touch a bit upon the mechanics of the evolution, the processes around how the language evolves. OCaml adopts an open process. Oftentimes I get asked questions, I mean, not I, but all the maintainers, that there are some secret discussions going on between the maintainers. Can we get minutes of the meeting? I mean, there are meetings, but we publish those meetings and they are very few, right? Most of the discussions happens on GitHub. So the compiler itself is developed on GitHub. All of the discussions typically happen on GitHub. You can go and see what each feature is being developed is and participate in the conversation, right? If you have something useful to say, you can participate. Everything is open, right? So we have RFCs, requests for comments of bigger features that we want to push. All of those are also publicly available. You can go comment on it. The compiler does have this multi-speed model. So if you have a small feature or a fix that you want to have, you go and make an issue saying, hey, this is broken. But you can also fix the feature and make a PR directly to the OCaml compiler. We will review it, discuss that, get it merged, right? And the catch here is that every PR needs a maintainer's approval. So we have these 27 maintainers. If you can convince one of them to say, okay, this feature is good, then we will get it in. There are certain parts of the language that require more than one vote. So standard library changes require 2 maintainers to approve it, right? So, but that's the only exception. Usually, if you want to add something and it's good, maintainers are okay with adding that. But there are larger features that require bespoke processes like publishing papers, right? Publishing extensive performance evaluation, even formalized semantics of soundness and such. I'll show you example of both of these. And the point to keep in mind is that when you have a problem and you have a one-line change which you think is the solution, the work is not done. So it takes a long time to actually go through the process. I want you to, I'll give an example where you can appreciate that process. So in C++ we have vectors, right? Vectors sort of give you constant time access to different indices, and then you can also append to the vector, right? You can grow. It's not a static array. OCaml did not have that feature for a long time. So it had static arrays, and then yeah, you have to know the size. Otherwise, you have to use some other structure. So obviously, this is like a missing feature, and some student observed that this feature requires to be implemented, and they proposed a very small change. So if you look at the initial PR, it's only 200 lines of code. They said, I added dynamic arrays to the language. Can you include it, right? And there was immediate observation that, okay, this is a feature that is useful to have. So a lot of the maintainers said, okay, this is a good feature to have. We sort of looked at the feature and found that the implementation needed a lot of room for improvement. So testing and coverage and all of that, API design was not good. But there was broad consensus that that feature needed to be included. So we immediately, the same day, we gave feedback saying, this is good, but we need to retry it. Of course, the student went away and never came back. But a couple of years later, one of the industrial users of OCaml, who is not a maintainer, came back with a very clean API, very nice design. This was in September 2022. You can see that the number of lines has ballooned, right? So it went from 198 to 792. It was a nice implementation, but multi-core was just around the corner. and we hadn't discussed what the API changes should be for multi-core and performance and safety. So we discussed this a lot. Yeah, you can see that there were 92 conversation comments here, and we decided we needed to simplify this. So we said we'll keep the performance question out of the first PR. We'll just focus on the API design, and then we'll do the performance later. So the very same day when this PR was closed, very close to, just before this PR was closed, another PR was open, this time by Gabriel Scherer, who is a OCaml maintainer. So he picked up the work. So couple of things to observe, right? So it's not like one person started, they are the ones who are doing the work. Somebody started, they found that it was a good idea, somebody else developed it, and then somebody else continued it, right? So open source works on sort of paying it forward, right? So so yeah, but you can see that the implementation is now ballooned a lot, right? 2000 lines of code. It's a nice clean API and a simple implementation. This was discussed again a couple of months, and it was merged. And the biggest question is how to name things, right, in computer science. Have you heard of the term yak shaving and all of that? So if people don't have good ideas, good things to say about something, they will just say, I don't like this name. You cannot ever go back on that, and it's a moot discussion. But once the API design and the naming and all of that got sorted, then we could actually focus on implementing it fast, right? So this was a couple of months after this PR was closed, rest of the work was done. Same clean API and optimized implementation that was merged, right? So if you look at the summary, right, the feature was itself proposed in 2019, and the two PRs were merged in 2024. Initially, it was 200 lines of code, but it ballooned to 2,500 lines of code, and there were 500 plus comments across the different PRs, right? So if you were thinking about, oh, this is a small feature, let me just add it. This is just a cautionary tale of how long it takes to get features into the language. I picked a deliberately bad example just to show you the social dynamics around it. If you are fixing a bug, it gets in very fast. If you fix a security vulnerability, same day, right? We'll all work all night and push it through. But the question you want to ask is whether this is all worth it. And the way we maintainers are thinking about it is, yes, it is definitely worth putting in this effort, because we want this code to work for the next couple of decades, right? We are not thinking about systems that work for next month, next year. So we have systems that have been working for the past 30 years, and they will continue to work, right? I want this code to work. If today you write a code with dynamic arrays, 30 years later, right, your children will write some code which is building on top of that. We want the same code to work, right? That's the way we've been thinking about all of this. And in open source, it's much harder to undo changes after you release it. Somebody will depend on that feature in some part of the code. You can't change it after a year. Oh, this was a mistake. So we have to be very careful when we sort of design this API and such. Yeah, so this was supposedly the small feature, right? But I also wanted to give an idea of, touch upon some research aspects as well. But this is a larger change that we wanted to push into OCaml. So this is a project that I led called Multicore OCaml. It aims to add native support for concurrency and parallelism to the language. Yeah, so we have different features for concurrency and parallelism. Concurrency is just interleaved execution of tasks, and you're essentially running on a single core here. Parallelism requires multi-core execution, right? So, and they are all simultaneously executing overlapped with each other. We have different mechanisms called effect handlers and domains for this. And this was a very large project. But the way to sort of think about this project is the sort of challenges that you have to have in mind when you undertake such a project, right? So when you build a multi-core version of a language, you need a multi-core garbage collector and a multi-core runtime system. I won't go into the details of all of this, but this is the guts of the language, right? And when you are going from sequential programs to parallel programs, you need to change a lot of things, including the core of how the language operates. And this is almost like replacing a car engine while the car is running, right? So you won't, hopefully you will not see any of this change as a user, but somebody has to do the work, right? And we also needed to give semantics for what it means to execute OCaml programs in parallel. Again, this is something that I won't go in detail, but OCaml is a statically typed language which says if your program successfully compiles, it will never crash. But this is very much not true with languages like C++ and Go, where you can have some concurrency bugs that will make your program crash very badly, right? As I used to joke, crashing is the best thing your program can do when it goes bad. It can do much worse things like leaking your password, opening up security vulnerabilities and whatnot, right? So in a way, what OCaml is trying to say is when your program compiles, it is definitely going to not have these behaviors which are undefined, right? So if you write some programs, it is not secretly going to allow for memory errors, right? So use after free such errors are not possible at all. This needed redefinition of the language semantics itself. So this was a big area of work that we had to do. And finally, right, even though we are adding this big feature into the language, we have to realize that 99% of the people are still going to write sequential programs. So just because you provide someone like a, I don't know, a big crane, right, doesn't mean everyone is going to use a crane, right? They might not need that crane at all. But some people are going to need it and they are going to use it. But if you say, oh, everyone gets a crane and they need to find a parking spot for it, right? People will be like, why? I don't even need it, right? So the analogy here is that if I say, oh, you can have this multi-core feature in the language, but all of your sequential programs are going to be 20% slower, that's not going to fly, right? So people care about their programs. Why should they pay the cost? They are never going to write parallel programs. So the thought process was that we want to maintain performance backwards compatibility and feature compatibility. So your existing programs which were working on the sequential compiler will continue to work on the parallel compiler and have the same performance behavior, right? This is extremely important when you design, think about language design and evolution. This is very, very important. It might, I mean, for many years this was the only thing that I was thinking about, but everyone else in the world has other things to think about, right? For them to say, oh, you can have multi-core, they will say, no, I don't want it. So you have to sort of make it so cheap that it shouldn't affect them. And for people who care, so it should provide the value. So we did many things here, but we are pushing a big change. So how do you build credibility with the maintainers, right? I am a maintainer, but I also need to build the credibility with other maintainers of the language. So I can't self-approve my own PRs, if anybody was wondering, right? That won't work. Yeah, we are even discussing something around the policies around conflicts, right? So what if there is another maintainer from IIT Madras and I approve their PR, right? So all these discussions are going on in the public, right? So you can go and read what the conflict resolution, yeah, so you can sort of think about, I mean, this is very similar to how academic conferences are run. When you publish a paper with your potential collaborator who you published a paper with, you won't review the paper, right? That person would mark you as a conflict. So we do similar things, but how do you actually build credibility for the work that we are doing here? And the way we did that is by publishing key results. I will tell you why publishing is important here, and a very rigorous evaluation. So we started out in 2014, right? I joined soon after the project was started. Our idea was that we will take the upstream compiler which is on GitHub, we would fork it, call it multi-core OCaml, we'll keep developing it and pulling changes from upstream. So just because you are working on a feature doesn't mean that the upstream is going to stop. They are going to add features, potentially conflicting features also, right? Now you have to think about how do I reconcile those two conflicts, right? So this went on for a while, and eventually you reach a point where it's good enough, right? And the plan was to upstream it one by one, small features, I mean initial big feature and then more and more features. This was the plan. We published a bunch of papers, right? And the reason why publishing papers for language development is useful is, so OCaml comes from INRIA, which is an academic research lab in France, and we really value academic rigor, right? So if you are saying this feature works this way, we really like formalized versions of the semantics, right? We really like strong implementation, evaluation, and so on. So publishing papers for us was useful. Just as an academic, it is useful to publish papers. But the reason this is important for language evolution is it sort of succinctly captures what we are trying to say. And typically these papers are also reviewed by the wider community, not just the people who are maintainers, right? So there is external validation for your ideas as well. And I think it helped a lot trying to publish these papers. So we published a paper on the multi-core runtime and garbage collectors, which won a best paper award. And then we published a paper on the relaxed memory. So this is the semantics for the language when it executes in parallel. And the last paper is this concurrency story, which I'll talk about a little bit. So I'll just dive deeper into this concurrency story. So concurrency is interleaved execution of tasks, right? And why does it matter? Why do we want to do this? What is the need for having this in OCaml? So I'm going to broadly define concurrent programming, very, very broadly, right? So it is where you might start a computation. Your computation may be suspended at some point and resume later. So that's my definition. And in fact, if you look at concurrent programming landscape, there are lots and lots of languages that provide concurrent programming features. Async await is provided by JavaScript, Rust, F# and whatnot. Coroutines are provided by C++, Lua. And you will even see that some languages provide many of these features, right? So if you look at JavaScript, it has async await, generators, promises, callbacks, all in the same language. You can write programs with everything, and nobody knows how all of these work, right? Their combination. They know how independent features work, but their combination, the semantics is not formalized. So it's often difficult to reconcile the meaning of, I've written a program, right? Whether it's correct or wrong, it's a definition of the semantics of how these features should interact. So we often don't have language to even talk about all of them in the same setup, right? So of course, there are many reasons for going for a cleaner approach. One very pragmatic reason for going for a cleaner approach is OCaml maintainers are all volunteers. So we want to keep the language small. We want to get the smallest, most powerful primitive into the language so that everything else is not a compiler concern. But the user should be able to build rich libraries on top, right? So find the best possible primitive that expresses the idea that you want to express. And you do a very good job of implementing that well. And everything else can live outside of the language, right? That's the philosophy here. So we did not want a zoo of primitives, right? Like what JavaScript has. But we wanted a smallest primitive that captures many of the concurrency patterns. I say many here because we won't capture everything. So trying to do all of it is not the right approach, but we want to capture many of the useful patterns, right? And the pattern that we came up with is effect handlers. Effect handlers are this mechanism for programming with user-defined effects. So they are a modular and composable basis of all non-local control flow mechanisms. Many of you might have used exceptions in C++, C++, Java, right? Few nodes, right? But you might have, if you've done any sort of JavaScript, you've done asynchronous programming with generators, asynchronous I/O. The point here is that if you have effect handlers in the language, then all of these features are implemented as libraries on top. So you don't have to put them into the language. And the meaning of how all these features interact is just through compilation. Because you are implementing it as a library, you clearly know what they are all implemented with, so you can reason about them in a same framework. So if you program with exceptions, effect handlers are nothing but first class restartable exceptions. So in an exception, you throw an exception, you handle it, and you're done, right? But what if you had the ability to sort of throw an exception, handle it, and then go back, right? That's what effect handlers provide you. The theoretical basis starts from this idea called delimited continuations. I won't go too deeply into that. But interestingly, they sort of enable various sort of features, right? You can do direct style asynchronous I/O, you can do resumable parsers, you can do things called probabilistic programming, which is a very nice way to describe probabilistic programs. The models of probabilistic programs, you can write it very nicely in this language. There are also yeah, you can do gradient descent, all sort of fancy things, right? Somehow this one feature is very powerful, and this was not our intention, right? But other people discovered these useful patterns. There are a bunch of examples in this URL, you should check it out. The thing that I wanted to focus on a little bit is to actually show you how this works. So this is the first time I'm showing OCaml code. I will try to walk you through this. I'm not expecting you to understand OCaml code a lot, but you should be able to take away the high level idea. So here is some OCaml code that is using effect handlers. So you have this notion of an effect declaration, just like an exception declaration. This effect declaration says I declare an effect called E, which when performed returns a string value, right? So that's one. And then I have this notion of a computation which is run in this try with block, and I have a handler which is handling the effect. We'll come back to this later. So as I said, we need a way to perform the effect to suspend the computation. So there is a primitive called perform, which performs this effect E, and the effect of that is that the computation is suspended, right? Whatever you're doing gets suspended. What does it get suspended to? It gets suspended to this effect handler, wherever the effect is handled. So I perform E, just like exception handlers, I handle the effect here, and the suspended computation between the point of perform and this handler is captured in this thing called a continuation. You can sort of think about this as I was executing some function, and I said pause this function halfway through, right? And you need a handle to this paused thing, right? And this handle to this paused thing is your continuation. That's your K. So now that you have a paused thing, what do you want to do? You want to resume it, and we have a primitive called continue, which is going to resume the suspended computation. So you call a function, typically it returns, but here what you can do is you call a function, the function can choose to suspend itself, and then you get a handle to the suspended computation. You can do fun stuff with it and eventually resume it when you think it is ready. Okay, so I'm going to walk you through the same example but done in a different way. I'm going to show you how it is actually implemented. So this is all implemented very efficiently in assembly code, but here is a take on how abstractly it executes. So I have the program counter on the left hand side, and we have the main stack with the stack pointer at the bottom. When you enter the computation, we create a little stack. This stack is very small, it's only 32 words in size. That is supposed to be the stack for executing this computation, and we create a parent pointer to the main stack. So our stack is now not just your usual program stack is a contiguous space, right, where you call and return. Now our stack is actually split. Where are they split? They are split at effect handler points, right? So the idea is that the split a priori allows you to suspend the computation efficiently. We'll come back to that. So you continue executing this program prints 0 first, and then it is going to now perform E. So what does perform do? Perform suspends the computation. The way you do that is you sort of create this continuation object on the heap, make it point to the current stack. The stack is known as fiber, right? So now you got a pointer to whatever was executing. So that sort of captures what you were doing back then. Just like exception handlers, you search for the closest matching handler. So there is only one handler here for E, which is in the main stack. So my control switches to the main stack. You get a pointer to the continuation, which is what you find here. And just like exception handlers, you run the exception handler itself. So when you handle exception, there is a function that you run. So which is what we start running here. Except that when you run exception handlers, you get the exception and nothing else, right? Here you also get this continuation, which is a handler to the suspended thing. So now I print 1. I want to continue. So what does continue do? Continue resumes the suspended computation. So where do I resume from? I resume exactly from this perform, right? If you remember earlier, actually it's here. We declared E to return a string when performed. So when you resume it, you also need to pass a string. So when you resume, first thing we do is we erase this pointer from this continuation to this fiber. So our continuations are known as one shot. This is a technical thing, not important, but essentially if you suspend, you can only resume it once. And then you sort of put the stack back to how it was and go back and continue with this value. So because you continued with 2, you printed 2 here, so we get 2 here, and then you resume, you will print 3. What happens after 3? My execution of computation has ended, and then it works just like how function call will return, right? Comp is done. Who called comp? Comp was called here. So you would expect this stack to be, this frame to be gone, and you resume, right? Oh, what's happening here? So the function is actually resuming not from here, but it resumed from the handler. This is a bit weird, but the way to think about delimited continuations is they are suspended functions. When you call a function, they return, right? I called it here first, but then I resumed it here. So my continuation actually returns from here. So you resume, you do the rest of the computation, which is print 4, and then you return. This is a minor technicality, but the way to think about continuation, especially a delimited continuation, is it's like suspended functions. You can suspend and resume. Wherever you resumed, that's where the control returns, because the function completed execution from that point. So if you resume the same function suspended multiple times, there are a stack of these, right? And each point will resume itself. Yeah, so that's the semantics of how these work. Now you can actually go ahead and build interesting things. So the primary reason why we wanted to implement this in OCaml is implement it for concurrency. I want to do concurrent programming. By concurrent programming, I want to create millions of threads, right? Not operating system threads, but threads that have essentially, it's a program organization mechanism, right? I can have millions of requests coming into my web server at the same time. I want to handle million requests at the same time. Each one logically has its own context. So at the language level, I want to be able to create million threads, but at the systems level, you can do whatever, right? I can even run it on one core. So we are going to implement what is known as lightweight threading. So this is the model that all the languages that use asynchronous I/O do. So in JavaScript, when you're doing async await, this is what you're doing. In Go, when you write Go routines, this is what you're doing. In Haskell, if people have programmed in Haskell, this is again what GHC threads give you. But we are going to implement our own library in maybe 15 lines of code, right? So this library provides 2 functions, fork and yield. Fork takes thunk, so it's like some function pointer. It's going to fork it abstractly in parallel. So that's going to run parallelly with respect to whatever you are running. Yield is just going to give up control, right? Whatever you are executing, I'm going to give up control. So this is the entire code. I've sort of dropped a couple of lines here. Essentially, what I have is a queue of continuations, and the main work is done by the spawn function, right? So the way to sort of think about this is, when you want to create like a lightweight action, right? I want to spawn this f concurrently. So I run f in an effect handler. There are 3 things that f can do. F can run to completion, right? Which means that I finish, but there may be other threads that are running. So I want to resume them. So I call run next. What does run next do? Run next looks at the queue of continuations, and then if there is a continuation, it resumes it. If there is none, then you're done, right? There are no continuations and you are done, so the program is done. But this computation may also try to create other threads, right? And try to yield. So both of these are handled as effects here. If you do an yield, you get a continuation here. In fact, the way to think about this continuation now is it's your handler, thread handle. So that's the currently running thread, and I want to switch to another thread. So I take the currently running thread, I enqueue it, right? And I call run next to run the next thread from the scheduler. And if you want to fork, you again get the current thread, you enqueue the current thread, and then you fork off a new computation by recursively calling spawn. The code is doing a little bit of magic here, but essentially if you sit and stare at it for half an hour, you will understand what is happening. This is usually thousands of lines of code in real systems, right? So that's the key takeaway here. And you can write nice high-level functions that just perform the fork and yield effect. So what do you get because of this? You can write high-level programs. You can say, oh, I have a main function that forks off 2 threads, that prints a couple of messages with a yield in between. So when you run this program, you actually get concurrency, right? So 1A is printed, then 2A is printed, then 1B is printed, 2B is printed, and your program is done. So we've actually created the concurrency with this one little feature, right? And the point is, user code need not be aware of FX. So this, for example, I could have implemented this fork and yield with real operating system threads also, but it doesn't matter for whatever the user is doing. User has a lightweight thread now, right? It acts like a real threading system. You don't get parallelism because all of these are run on the same core. That's a separate problem. And the point here is many languages already do this. So Go language and GHC and even JavaScript already have support for this, but they're all primitives in the language. So they are implemented as part of the language. If you wanted to, so GHC and Go use work stealing scheduler with a round robin thing with a FIFO queue. If you wanted to, so we used a queue, right? If you wanted LIFO order, you just go back and change that little data structure and you're done. So this is all like under your control, not the runtime system's control. So this is what I mean by saying find the smallest primitive and then other people, I mean you can implement all of these as libraries, right? This is not a toy, right? We've implemented a full-fledged asynchronous IO library called EIO. Several industrial users are using it already. And there is this wonderful new operating system innovation in Linux called IO Uring, which is a general purpose asynchronous way of communicating with the kernel. So typically when you do system calls, right, you call the system, you make a system call, there is all of this overhead for system call, then you context switch back. But IO Uring allows this shared ring buffer where you keep putting in requests for the kernel actually asynchronously takes the requests off and returns the results in a different ring buffer. So you can do lots of communication with the kernel without having to go through the system call interface. It's great for IO and we have an implementation of that. If you want to use IO Uring, it's very complicated API. We sort of wrapped all of that around EIO in a similar way. Whatever I showed you, it's all very high level. We can have all of the complexity in the backend. And here are some results. Yeah, you can make graphs tell anything that you want. So don't take this as the like, okay, it's fast or it's slow. There is one particular workload where we have, it's a web server, it's a full-fledged web server, right? Where we are measuring the throughput of the web server. So we are issuing requests here up to 400,000 requests per second, right? And we are looking at how many requests are satisfied. You can look at this and see that EIO is flattening out at 200,000 and Rust Hyper is flattening out at 175,000. So there are people in this room probably, yeah, who are working on reproducing this again. The results are a little bit different, but roughly the same sort of thing holds. In a way, what I want to sort of get across with this graph is, it's not that these high-level abstractions need to be slow, right? You can be extremely fast. You don't have to, I mean, Rust people will argue very hard that, oh, you need all of this to go fast, right? I think there are like 99% of the problems you can do it with high-level abstractions. Of course, there is this last 1% where you need to bridge the gap. And for that, you need tight control. And in fact, this is another thing that's very new. So Jane Street, which obviously are using OCaml a lot, they've been using effect handlers for hardware simulations, right? And I don't know hardware simulation. I never had hardware simulations as a thing when we designed it. But they found use for using effect handlers for hardware simulations, and they use it as part of the HardCaml library. So again, the principle here is that if you design one thing well, other people will find use for it. You don't have to know what the uses for those are. This is very new. This is like within the last 2 weeks. I don't know anything about hardware, right? And yeah, so this person doesn't know anything about type theory. So what he's saying is, I am writing this post as someone who is not a type theory expert. The fact that I can use algebraic effects without fully understanding the underlying mechanics is one nice feature of their design. So as long as you have this nice abstraction, people who are working on hardware can use this. And I don't know anything about this. I didn't design it for them. But they say that they can be repurposed and it's a general language feature. That's what you're looking for when you design. That's what programming language design is about, right? You come up with these little abstractions that talk about one thing and one thing well. yeah, if you like this, there is a very nice book, open source book written by Xavier Lewa that talks about all sort of control structures, right, from Goto to algebraic effects. Very nice book, very nicely written. I'm close to the end, but I'll quickly go through. So, in order to, I mean, all of this was because we wanted to upstream OCaml, and building this language feature, publishing results is not just the only thing that you need to do. When you do this for real, you need benchmarking. So, we built a full-fledged benchmarking infrastructure called Sandmark, which continuously benchmarks the compiler, the vanilla compiler and the multicore compiler nightly on various platforms, right? This is a lot of work. It's a very big distributed system. We built this. It was running for a long time. We're going to try to revive this soon. And yeah, you also want to look at the whole ecosystem, how it works. So we built this thing called OPAM health check, which is the package universe of OPAM packages that build on the existing compiler and which build or not build on the new compiler. And when you see a green, the package builds. When you see a yellow, one of the dependencies breaks. When you see a red, that package breaks in this new compiler. Most of these were nothing to do with multicore. When you do a major release bump from 4 to 5, people take it as a good reason to remove all the deprecated features. They will mark something as deprecated and they will say, now this is no longer used, right? They are going to remove it from the compiler. Most of these were easy to fix. So we fixed all of them. The point that I wanted to make is you can contribute to compiler development without actually hacking on the compiler. So again, this is a very big distributed system, right? And if you are interested in different parts of it, you should be able to hack on these parts as well. OPAM health check runs today. It's open source. It's there. If you want to go have a look, you can go have a look. Yeah, actually OCaml 5.0 was released, but when you say released, it's not done. It's like asymptotically tending towards completion. There is always more work to do. We've been slowly working on fixing the last couple of features. So the next thing that we've been working on is something called OCaml, which is to bridge this gap between OCaml and Rust, right? So there is a lot more in this, but OCaml is interesting in the way that so Jane Street, the company trades in the markets, but they also have a very good PL research group, which actually builds the compiler, and they use the compiler in production, which is very strange, right? They have this very bleeding edge feature which they are using for trading trillions of dollars, and the way they can do it is because all of the code sits in a monorepo, and if they make a mistake, they can roll it back very quickly. But none of the mistakes are like fatal mistakes, right? So they are mistakes which are design mistakes. It's very interesting. It's a very interesting way of doing language design, which we have not seen previously. They've also been publishing lots of papers. Eventually, all of this will land in OCaml. In how many years, we don't know, right? But they're all there. If you want to learn all of this, you still have time to sign up for my course, half an hour. I mean, we'll discuss this and more, right? So 6868, please do take it. And we've launched this thing called FP Launchpad, which is systems hacking, and all of this is like lots of fun, right? So we are dealing with semantics, and we are dealing with implementations, we are dealing with benchmarking, open source. There's a lot to be done here. So our goal is to build research and educational capacity for efficient, reliable and trustworthy software. We want to do it in, it's not just about research, it's not just about training, right? It's a hand-in-hand thing where research, training and actually building real systems, right, people care about, right, and produce it in a state where it's industrial strength and open source. So we want people to start using it, right, and using it, and then it feeds into research problems. It may feed into other things that we want to push for, like we have a bunch of education and training initiatives which I'll roll out. If you are interested, come do talk to me about this, talk to you about opportunities that we have. Yeah, there's a bunch of ways you can get involved in this. You should, we have a Discord, we now have a Zulip channel as well, where the developers are also discussing publicly in not an async, it's a semi-sync fashion. There's a lot of these, I mean, the thing that I wanted to say is a lot of these are all already public and open, right? You can just go and participate. There is nothing stopping you. right? So if you want to go, you can go participate. In fact, you can just go to the OCaml GitHub repo and see good first issues, start fixing it. And yeah, we are always looking for new people to contribute to the compiler. And if this sort of thing interests you, you should, right? I'll stop there.